So, as you guys might have heard in class so far and learnt in year 11, if a curve is sloping upwards, reading it from left to right, then the tangent has a positive gradient, or the curve has a positive gradient. And then if our derivative at point A is greater than 0, then we say that the function f of x is increasing at that point at x equals a. So if we consider this point here that we have in this diagram, point A, the derivative at point A is going to be greater than 0, and therefore that means that the curve is increasing. So, conversely, if a curve is sloping downwards, reading it from left to right, then the tangent has a negative gradient. And so if the derivative at a point A is less than 0, then the function is said to be decreasing at that point. So a review of all of that is if the derivative is positive, the curve is increasing. If the derivative is negative, then the curve is decreasing. And this is how we can use the derivative to know things about the curve itself. Know whether it's increasing, decreasing, what the gradient is, etc. So, the third circumstance that can happen with a curve is if it's flat. So it's not increasing, it's not decreasing, it's flat. And at that point, the tangent has a gradient of 0. That makes sense, right? Because it's kind of in between the positive and negative gradients that we were discussing before. So, if the gradient of a function at point A is equal to 0, then the function is called being stationary at that point x equals a. So in all of these scenarios down here, we have curves that have a gradient of 0 at a particular point. So here the gradient is 0, here the gradient is 0. Here we kind of have this chair-shaped function, which is what you might typically see in maybe like a cubic polynomial, I mean. We have this stationary point of inflection in these scenarios here as well. And in all of these scenarios, we have a stationary point because instantaneously, just for one tiny second, the gradient is 0 and the curve is flat. So as you can see, we kind of have two categories displayed here of stationary points. We have turning points, and then we have the points of inflection. And this is where the curve kind of has that chair shape. So now we're getting into how we can use the second derivative to know things about our original curve. And again, don't worry if some of this is kind of going over your head a little bit. We'll go over some examples in a second, which might help you understand. And again, if I'm going too fast, you can absolutely pause the recording. Yeah. So, as you can see, we have our diagram here. So this curve here is the original curve, y. This curve underneath is the derivative, y dash. And this third curve here is the second derivative. So, as you can see here, and this is kind of a visual representation of what we've been going over so far, the curve here, I'll draw it in for you guys. The curve in this section has a positive gradient because it is increasing. And then also here, it has a positive gradient. But in this middle section down here, it has a negative gradient because it is decreasing. So when we look at our derivative curve, the value of the derivative is actually positive in the two sections corresponding to the positive derivative. So in this section here, our derivative is positive, and then this section here, our derivative is positive. And then in the middle section in here, our derivative is negative because it's below the x-axis. And as you can see, these sections correspond to the original function. And this is why if our derivative is greater than 0, then we have a positive gradient or an increasing function. Because as you can see, when the derivative here is above 0, the value of the derivative is above 0, it's above the x-axis, this is when we have a positive gradient. So this is where these kind of rules come from that we were discussing before. And this is a visual representation of them if you ever need to use one. If you're maybe using the graph function of your calculator, it might be a little bit easier in a tech active exam. This is how you can tell. The other thing that I would like to point out to you guys is that we have these two stationary points here and here. So this is when the curve is kind of turning around. It has these two turning points. And corresponding to the x value of these two turning points, we have an intercept of this derivative curve with the x-axis. So remember how to find the x-intercept of a curve is when the value of the curve, or the y value of the curve, is equal to 0. So when the derivative function is equal to 0, we have a stationary point. So all of these rules that we've gone over in the previous slides have these graphical representations which really help to kind of understand where they're coming from and really help to remember them and also to apply them in graphical situations, like if you're doing, as I said before, a word question in your graphics calculator where you're kind of graphing a function or something like that. It's really easy to tell when the function is increasing, decreasing, or has a stationary point just by looking at the graph. Now, getting into the relevance to the second derivative. So, remember the second derivative is the derivative of the derivative. So the second derivative tells us about the properties of the derivative function, but it also tells us about the properties of the original function, y. So we're going to go over those now. So as you can see here, our second derivative has a positive value here, and it has a negative value here, and then it also has this x-intercept right in the center. So what we can firstly recognize is that this positive portion of the second derivative corresponds with the section of the first derivative that has a positive gradient, which is exactly the relationship that we saw between these two. But of course, because the second derivative is the derivative of this function, we can also see a similar relationship. So when the value of the second derivative is positive, it means that the gradient or the first derivative function is increasing. And then a similar thing here. So in this section where the second derivative is negative, the first derivative is decreasing. Same thing again, where the first derivative has a stationary point, the second derivative is going to have an x-intercept, and this is exactly what we saw up here. Now, the other thing that I want to point out, and this is kind of the more typical application of the second derivative, is its relationship with the original function. So, what I want to point out to you guys is that the second derivative tells us about the concavity of the original function. So, when we're talking about the concavity of the original function, we are talking about whether its gradient is increasing or decreasing. And I'm going to draw a second diagram over here. And this is of the original function, y. So, as you can see in this section here, so even though the gradient of this function is kind of what we've drawn over here, the gradient of the function and the actual concavity of the function are not the same thing. So, as I said, the concavity tells us about whether the gradient is increasing or decreasing. So, in this section here, the gradient is decreasing. So even though in this little part, in this part here, the gradient is positive, the gradient itself is decreasing. So the gradient is getting smaller and smaller. It's getting less and less positive. And this is because down here, the gradient is really steep. But as it's coming closer and closer up here, it's getting more and more flat as it approaches the stationary point. So it's really, really steep down here and getting more and more flat. It's getting closer and closer to zero. So even though the gradient itself is positive throughout this entire section, it is actually getting smaller. It's getting less and less positive. It is decreasing. And then as you can see down here, the gradient is still decreasing because it's getting steeper, but it's getting more and more negative. So even though the gradient might be -1 here, it might be like -10 here. It's getting smaller and smaller. However, at this point here, the gradient actually stops decreasing and it starts increasing. So it changes. So from here onwards, the gradient is actually getting more and more positive, and that's because even though the gradient itself is negative here, it's actually approaching zero. So it's really steep, but it's getting less and less steep, less and less steep, less and less steep, and then it gets to zero here. So it's getting closer and closer to zero. It's actually getting bigger throughout this whole section, and then as it comes up here, the gradient is positive again, and then the gradient is actually increasing again. So it's getting steeper and steeper. It's getting more and more positive. So as you can see, these two arrows tell us about the concavity of the curve, and this is the rate at which the gradient changes, not the actual gradient, whether it's positive or negative, but the rate at which it changes. So as you can see here, this section of the function has a certain concavity because the gradient is decreasing. And then in this section, the gradient is increasing, but then we have this point in here where the gradient changes from decreasing to increasing. And this is called our point of inflection. So if you have a look back over at our diagram over here, we're looking again back at our initial function related to our second derivative. our second derivative is negative, so it's in this negative section. In the section where the gradient is decreasing, so this section in here corresponds to this section here. Then at this little dot in here, this is when the second derivative has an x-intercept. So as you can see in here, this is the point where the concavity changes, and this is when the second derivative has the x-intercept. And again, when the initial function is increasing, then our second derivative is above the x-axis. So this tells us a lot about the concavity of the curve. And I hope this visual representation really helped you guys. I know we went over that kind of in a lot of detail, so I hope that if you already understood that, it consolidated it, but if you didn't, it really helped you understand. I know it took me a little bit to get all of this stuff, all the relationships between the different curves, kind of mess you over a little bit just to begin with, but I hope this really helped you guys. If you're still having trouble with it, maybe rewatch this section of the recording. But okay, now we're going to get into the relationship between the first and second derivatives, kind of in a more structured approach. So, as I was talking about before, we have two types of concavity, when the gradient is increasing and when the gradient is decreasing. So, as you can see here, in this section, the gradient is increasing. It's becoming more and more positive. It kind of has this curved shape. And we call this concave up. And this occurs when the second derivative, this is the notation for the second derivative that we can also use as well, if you haven't seen this before. This is just another way of saying like y double dash. When the curve is greater than 0. And then we have concave down when the derivative is less than 0. So these two are kind of the most archetypal examples of concave up and concave down. So as you can see here, throughout this whole section, the gradient is increasing. It's becoming less and less negative throughout here. It's becoming 0, then it's finally getting more and more positive. And then in this section here, the gradient it's positive here, but it's getting closer and closer to 0, and now it's finally getting more and more steep and more negative. And this is concave down. An easy way to remember this, and this is how I remembered it in year 12, was that when we're talking about concave up, I just remember it as cup. That was terrible handwriting, I'm very sorry. But I remember it as cup, concave up, and as you can see, like all of the curves that we've been shown for concave up kind of have that, like, they look like they would, if you kind of rained water down on them, they would catch the water. That's kind of how I think of it. So even though this section here does kind of look like a cup, but these two sections here don't really look like a cup. But if water came down here, the two curves would capture the water, sorry. And then concave down occurs when the curve would deflect the water. So in all of these scenarios here, the water would kind of just rain on and then fall off. That's how I think of it. And yeah, as you can see, these two requirements for concave down and concave up, we can also see in our graphical representation. So when the second derivative is positive, is above 0, it's going to be increasing, and that's what we saw back here. So when the second derivative is positive, then the curve has this concave up form and is increasing. And when the second derivative is negative in this section here, then it's going to be concave down, it's decreasing. This is just an overview of the notation that we use, just to refer back to if you're ever having trouble or don't understand a question. So remember, if the function is given in y, then we can differentiate this with respect to x to get dy dx. The second derivative is expressed as d squared y dx squared. And look, I'm going to be completely honest with you. I do maths at a university level, and I still don't remember where the squareds go on this second derivative. So I would recommend just kind of practicing it and do a kind of a rote learning approach, because I still do not remember it. And if our function is given in y dash and y double dash, the y double dash is the second derivative, and then similar thing applies for f of x. So pretty simple once you get used to it, but maybe something that would be helpful to pop in your notes as well. Okay, so now we're getting into why the second derivative is useful. So, as I was going over before, the second derivative tells us about the concavity and the inflection points, and this kind of tells us information on how to draw our graphs, how to graph functions, like you might be asked to in an exam. Graph f of x and I'll give you a function. If you can find the concavity and the inflection points, it makes it so much easier, and tells you about the shape of the graph. We can also use the second derivative in optimization problems, which we'll get to a little bit later in the lecture. And then the second derivative also tells us about the relationship between acceleration and displacement, which we'll also get to later in our motion topic. But yes, so the second derivative is really important, gives us a lot of information about different topics. Okay, now we're getting onto some examples of finding the second derivative. So, in the first example here, we have the function x to the power 7. We need to find the first derivative. So remember the first derivative, we're just going to use our power rule. We're going to take the power out the front and decrease the new power by 1. Then remember our second derivative is the derivative of the derivative. So we're now going to derive this function here. So we're going to take that old power 6 out, reduce our new power by 1. And this is going to give us 42 x to the 5th. Now, in this second question here, we're going to need to find the first and second derivative. This one is a little bit more complicated because we have our x on the denominator of a fraction. A tip, which I haven't written down these slides here, but a tip for you guys in general when you're deriving and also when you get to integration, if you haven't gotten to it already. If you are deriving or integrating a function where x is on the denominator, you need to apply your index rules to get it up to the numerator, to get it in a format that you can derive or integrate. So the index rule that I am talking about is this one, and I'll write it over on the side here. It's if you have something with a power on the denominator, you can take this up and just change the sign of the exponent. And so kind of what this means, by extension, is if you have something like 1 or 3 to the negative 2, this is equal to 1 over 3 squared. So you can just change whether the number is on the numerator or the denominator by switching the sign of its exponent. So we can apply this in our question here. So we want to take it up to the numerator, so we're going to change the sign of its exponent. So this is going to give us x to the 3. And now we can find the first and second derivative. So the first derivative, I'm going to take that power out, reduce our new power by 1. Our second derivative, we're going to derive the first derivative here. So we're going to take that old power out and reduce the new power by 1, leaving us with 6x. Okay, that was a really quick example of finding the first and second derivatives. Now we're going to get onto an application of using the second derivative to find when a curve is concave up or concave down, and also using the first derivative to determine when a curve is increasing or decreasing. So we're going to be using the rules that we went over previously in the lecture, telling us about, like the value of the first and second derivative and what that tells us about the curve. And we're also going to be needing to derive the curve. So what tells us if a curve is increasing or decreasing is, remember, the first derivative. So we're going to find the first derivative over here. So we're going to have 6x squared, take 6x, take 12. And then what tells us if a curve is concave up or concave down is the second derivative. So we're going to find the second derivative as well. And this is just going to be the derivative of our first derivative here. So we're going to have 12x minus 6. So now we're going to need to apply the rules that we learned previously. So remember, when a curve is increasing, it means that the first derivative has a value above 0, and when it's decreasing, it means the first derivative has a value below 0. Now, we can solve these using inequalities. In my opinion, it's not super necessary to learn inequalities. It still really is useful. We're not going to go over it today just because it's not super necessary, but if you are more of a high achiever, I would recommend learning it. Today we're just going to use equal signs and then kind of find the rest of the answer from there. So, we need to find when the first derivative is going to be equal to 0, and then we're going to find out, like, if it's increasing or decreasing on either side. So we're going to let our first derivative equal 0. As you can see, this is a pretty simple quadratic. Because it's equal to 0, we can cancel these. So we're going to get x squared, take x, take 2. So this is a pretty simple quadratic. You would be able to solve this using your ACB method or by completing the square. I'm just going to do it on my calculator really quick because we only have 2 hours. And this is going to give us that x is equal to 2 and negative 1. So, sorry, I wrote negative 2. No, I didn't, that's an equal sign. Having a brain blank. Yeah, so our x is going to be equal to 2 and negative 1. So now what we need to determine is in between these intervals if the value of the gradient is greater than 0 or less than 0. So what I typically like to do here is use kind of a little table of values. So we are going to be finding out x in relation to the derivative. So we're going to have negative 1, 2, and then in between we're going to have other values, just any value in between these two, because this is going to tell us when the function is increasing or decreasing around those points. So we are going to sub our values into the first derivative. So we are going to have, so our derivative in this section here is going to be positive. It's going to be 0 here, negative in here, 0 again at 2, and then positive again at 3. So what this tells us is that the function is going to be increasing. Function of x is going to be increasing for the interval when x is less than -1 and when x is greater than 2. And then the function is going to be decreasing for the interval between -1 and 2. So the inequality signs that I'm using here are strict inequality signs, which means they just like less than, greater than. They don't have the equal to component as well. And that's because at the limits that we're using, -1 and 2, the function actually isn't increasing or decreasing. It has a gradient of 0. So that's why we're using those signs instead. So what this tells us is that the curve looks, something a little bit like this. It's going to be increasing for a certain section, then it's going to be decreasing, and then it's going to be increasing again. And this is going to occur at -1 and then 2. Because as you can see here, the gradient is positive up until it hits -1. Then it's negative between -1 and 2, and then it's positive again after 2. Okay, now we're going to use the second derivative to tell us about the concavity of the curve, and hopefully this kind of matches up with our visual representation of what we've got so far. So, remember, a curve is going to be, we can determine if a curve is concave up or concave down based on the value of the second derivative. So let's find when the second derivative is equal to 0. So the second derivative takes 6. 6 equals 12x. X is going to be 6 divided by 12, which is going to give us 1/2. So now we need to determine what the value of the derivative is, of the second derivative is, sorry, on either side of this point x is equal to 1/2. So we're going to use a similar table of values. So we are going to have x being equal to 1/2. Then we're just going to pick two values on either side. So we're going to have 1 and 0, because these are the simplest ones. So at x equals 0, our second derivative is going to be negative. It's going to be 0 to 1/2, and then at x equals 1, the second derivative is going to be positive. So we can apply this to our graphical representation here. So in the middle, in between -1 and 2, we're going to have our point 1/2. And then In this section here, our second derivative is negative, which tells us the curve is concave down. And that matches up with what we've drawn here based on our first derivative. And then after a half, it's going to be concave up. So our answer as we write it is going to be that our curve is concave up when x is greater than a half, and it's going to be concave down when x is less than a half. And again, when using our strict inequality signs, because at a half, the curve isn't concave up or concave down. It isn't either one of them. So we have to use our strict inequality. Okay. Now, that was the end of that question there. So now we're going to get on to a little bit more about points of inflection. So, remember, points of inflection change us when tell us when there is a change in concavity. So it is calculated when the second derivative is equal to 0. And that's what we saw in the last example, right? We found when the second derivative was equal to 0, and then kind of at that point, that's when the point of inflection is, that's when the concavity is going to change.